First of all, again, we're going to review what is the stoichiometry. Okay, yeah. So let's look at one of the questions. And again, a lot of people said, I understand how to do the calculate the stoichiometry, but when I read the questions, I have no idea how to solve. Okay, because I don't know where to start. Okay, I read a question, but I have no idea what a question it is. Okay, so what is this situation? In this situation, that means some parts you don't understand. Okay, yeah, there's a several different, like a limiting region question, stoichiometry question, or something else. You probably don't understand. Okay, what is the difference between each of us? And then even you have the equations, or even you write things on your notes, you still cannot solve, you see? Yeah, so chemistry is not just doing the calculation, and it's not just doing the memorization. Chemistry, you have to understand the concept before you're doing anything. This is the most important parts. Okay, yeah, you understand the concept and then apply the concept into the calculation. All right, so let's talk about the stoichiometry here. So 12, what is the total mass in grams of the product when 2.2 gram of the propane is burned in excess oxygen, which means we have enough oxygen, so we don't have to worry about. And then that means if we use up all the 2.2 gram of the propane, how many gram of the product that can be generated, right? So obviously this is not a limiting reagent question, because this question only telling you we have a 2.2 gram of the propane. We're not talking about the oxygen, because oxygen is unlimited. They have excess over here. So that's why this is just a stoichiometry. Okay, well, what is the backbone of the stoichiometry? Stoichiometry is using the coefficient on this equation to figure out the moles of the others. Again, it's in mole. If you have the mole of something and you figure out the moles of the others, it's not in gram. So the first thing when you solve this, you have to convert every mass into gram first, or into mole first, because we're only using mole. We're not using any others. Okay, so this is give you the thought. Either you're doing the step-by-step or doing the long equation. The first step is making that in moles. Okay, making anything in moles. At least this is what I learned when I was at college. When I look at the question, my first thought is I'm going to convert the mass to the mole. This is my first thought when I learned this stoichiometry. Okay, yeah. So now here it just talk about, okay, if I'm using up that much of the gram of this, and how much gram of CO2 they generated, how much gram of the water generated, we add them together, that's going to be the total mass of the product. That makes sense, right? So let's say, first of all, we need to figure out how many mass or how many mole of that. Okay, yeah. Either you set up the two equation, then you solve. Now we have a 2.20 gram of the propane. Now you're going to convert that to the mole. Again, mass over molar mass, you got a mole. The molar mass is a 44. So you have a 44.0 gram of the methane, and a 44 gram of the methane based on the molar mass. That much of the mass equal to 1 mole of the propane. So you have a 1 mole of the propane is equal to 44.0 gram. This is the meaning of the molar mass. 1 mole of this compound, those molecules add together. That's the mass of those molecules add together is a 44 gram. That is the meaning of the molar mass. Okay, yeah. So the mass you cancel out now after this 2.20 divided by 44. You know this is in mole, right? Mole of the propane. And then what are you gonna do based on the stoichiometry? Well, this question didn't give you the stoichiometry. You're gonna balance this first. So that is the stoichiometry. 1 mole of the propane will generate 3 moles of CO2, and 1 mole of the propane and also will generate 4 moles of the water. Okay, so now let's first figure out how many moles of the CO2 that we can generate. Since you have a moles of the propane, we need to convert the moles of propane to the moles of oxygen, right? 1 mole of the propane generates 3 moles of CO2. That means 2 moles of propane generate 6 moles of the CO2. That makes sense, right? 3 moles of propane generate 9 moles of the CO2 because this is 1 to 3, 1 to 3 ratios. Okay, if you're set up in the equation that has 1 moles of the propane is going to generate 3 moles of the CO2. Why are we doing this? It's because we try to cancel the moles of the propane. And we want to get moles of the CO2, okay? Yeah, well, if you're just based on the stoichiometry, you can also know, okay? You just times 3, you got the moles of the CO2. Does it make sense? This is also how we set up. You times 3, okay? But if you write everything over here, it's more straightforward to see, okay, why we are times 3, not divided by 3. You understand what I'm talking about? Okay, yeah. All right, so now you got the moles of the CO2, and then what we do to get a mass? Mole times molar mass, you got a mass, right? So you turn the molar mass of the CO2. The CO2 molar mass is also 44 gram per mole. This is a molar mass of CO2. For the water is 18 gram per mole. So you time molar mass of the CO2, which is 44 gram of the CO2 times 1 moles of the CO2. Okay, so now moles of CO2 are canceled. This setup will give you the moles of the grams of the CO2. Okay, so if you do the calculation, the result should be 6.60 gram of the CO2. Okay, well, we got a moles a gram of the CO2. Then we based on doing the same thing to figure out the gram of the water. Again, we have a 2.2 gram of the CO2. Sorry, a 2 gram of the propane. Okay, you're doing the same thing. Okay, we're gonna divide by the molar mass of the propane to get the moles of the propane. And then based on the stoichiometry, 1 mole of the propane will generate 4 moles of the water. So 1 mole of the propane is going to generate 4 moles of the water. Okay, so now moles of the propane canceled, gram of propane canceled. Now we got moles of water. Again, if you once got moles of water, you multiply the molar mass, you got the mass of the water. So 18 gram of the water is equal to 1 moles of the water. So the moles of water are canceled. Now you got the molar mass of the water. Okay, you got a mass of water. So you're based on this calculation, you figure out that's going to be 3.60 gram of the water. Okay, so that is how much gram of the CO2 that you can generate based on the propane, mass of propane. And that is how much gram of the water that you generate for the how much of the propane. And this plus together will be the total mass of the product that is generated from the mass of the propane. You may ask, hey, how come I only have a 2.20 gram of propane? How come I can get it more than 10 gram of the product? Why not? Why not? We have oxygen. Oxygen is enough, right? You didn't count the mass of oxygen. If you count the mass of oxygen in there, then you will have that much of product. Okay, yeah, so this is the stoichiometry question, and this is how we do this. Okay, in the lab time, not today's lab, but in the future's lab, we're going to do another kind of stoichiometry, which is solution stoichiometry, where we're using a molarity in there. We're using molarity in there. So you're gonna hear the molarity more often in the lab. Okay, you're gonna hear molarity more often in the lab.
Can you start the screen? That one.
Okay, so again, if you have a hard time, still have a hard time on stoichiometry or limiting reagent, let me know, because this is very important. We're going to repeat again in the Unit 3 exam. Okay, yeah, it's not just a one-time test. You're gonna have several tests that we still have 2 more tests. We're doing the Unit 3 in the next month, and then we're done for the unit exam, and then we have a final. Okay, we have final. Okay, so and just let you know, each of the exam definitely there are gonna be stoichiometry questions in there. Okay, yeah, so you have to understand what is the meaning of that. Okay, if you still have a hard time, you need to let me know. I will help out. I hope I can help you out. Okay, yeah. Okay, maybe it's just a little bit of twist. You're stuck there, and then you never go through. Okay, yeah, just like you clean the pipe, just a little bit of part you're stuck. It's stuck, and then never go through it. Once this part is being clear, and then you should be clear everything. Okay, yeah. So that is why I hope you can ask me questions, because those are the tiny bitty part. I think maybe it's okay. I mean, it's a common knowledge, but your maybe it's not good. It's not common for you. So that is why you have to ask me if you have a question inside. Okay, yeah, and if I clear that, you should be able to solve the problem very easily. Okay, yeah. Okay, so now we're going to talk about unit 3. Okay, unit 3 is talking about the thermal chemistry. Thermal, that means anything related to the energy, anything related to temperature. Okay, so that's the thermal part. So this is a kind of the chemical chemistry is involving energy plus temperature. Okay, so that is called a thermal chemistry. Okay, so before we talk about the real application, we need to talk about some of the concept. Okay, yeah, and those are the concept we have to understand before we doing any of the application. Okay, thermal chemistry. First, let's talk about some of the concept. The first one is called the system. The second one is called the surrounding. Okay, system and the surrounding, those two are coupled. Okay, and those two are coupled. The definition for system is talk about is the part of the universe we're watching. Okay. And the surrounding is talk about is the rest of the universe, the rest of the universe other than system. Okay, so those two concepts is it's not hard to so for example, if we talk about if we have a box over here, okay, and here is the system is called the part of the universe we're watching, which means if we have a box over here, we're watching what happened inside the box. So we're going to talk about this box is a system. For the rest of the others, not including the system, is called the surrounding. Okay, so generally system and the surrounding is how the people define. Okay, or if we want to observe what happened, what are the chemical reactions, what happened inside of this room, and we assume this room is going to be called a system. Okay, and the rest of the others, not just this building, but the whole world, whole universe is called the surroundings. Okay, yeah, so what you're watching is called a system. The rest of the others is called a surrounding. Does it make sense? Right? Yeah. So system and surrounding, okay? Yeah. So the system and surrounding, those two are interact to each other's, Okay. So here is the definition about the system. And for the thermal chemistry here, we're talking about energy, but the only energy we're talking about in thermal chemistry here in the Chem 1 is talking about only heat. Heat is one kind of the energy that we talk about. So the next one is the heat. Okay, heat is the energy. Okay, heat is also energy. In chemistry, sometimes we call there's other different kind of energy, but we only talk about heat in thermal chemistry so far over here. Okay, yeah. There's another two energy, you've probably heard that before. It's called kinetic energy. Then the other one is called the potential energy. Okay, yeah, but the kinetic energy, potential energy, we're not focused on those two energies. Okay, you probably heard this from the physics, kinetic energy, which means everything is moving. Okay, when the object is moving, they are having the kinetic energy. Okay, yeah, we also talk about the kinetic energy in chemistry, but not here, not thermal chemistry. Okay, yeah, we're going to talk about when we talk about the gases. Okay. Potential energy, we also talk about in chemistry. Potential energy in physics, it talk about, okay, so if you have a lift up some of the object, the object is potentially going to drop, right? All the kind of object will drop. And this kind of the energy, we call this is a potential energy. They have the potential to making this energy, okay? So in chemistry, we also talk about potential energy, but that energy is the energy that is stored in the bond. But we're not talking about this here, okay? But just realize we do have those two different kind of energy, but we're not talking about in thermal chemistry, okay? Yeah. In thermal chemistry here, we're only talking about heat. Heat is also energy, okay? We're using small q to represent heat, okay? We're using small q to represent heat. Heat is the energy, and this energy is used to change the temperature of the object. Okay, so that is the definition of the heat. So this is the concept. Okay, what is concept? Heat, first of all, heat is the energy. Okay, so you cannot see the heat. Can you see the heat? No. Heat is not a matter. Heat is the energy. You cannot see the heat, but you can feel it, right? You can feel it. So heat, this is energy, but this energy is used to changing the temperature. So if you see the temperature, doesn't matter, it's room temperature, your body temperature, the temperature in the refrigerator, the temperature, anything. Okay, any object has a temperature, right? So the temperature change for the object, that means the heat will change for this object. Okay, yeah, and the heat is used to changing the temperature of the object. If you see the object changing the temperature, then that means the heat. Definitely, we're going to increase or decrease the heat on this object. Okay, and then let's see the heat flow. Heat will have a flow. Okay, heat can be transferred from one object to the other object. Okay, heat can be transferred, have one object in the other object, but they have the rule to transfer the heat. The heat flow must be always from warm object to the cold object. Okay, so the heat flow always from warm object to the cold object. That is the heat. Okay, so the heat flow, they always transfer from high temperature something object to the low temperature object. Okay, yeah, so that is the higher temperature, lower temperature. Okay, well, then you may say, okay, so we have a very hot object. Okay, so for example, you're using microwave to heat up the hamburger. Okay, as the hamburger is getting warm, but for a while, the hamburger is cooling down, right? The temperature of the hamburger is cooling down, and then where the heat go? You said go from high object. Okay, high object, that's hamburger. And where's the low object, low temperature object? Is transferred to the air. Air is also an object, okay? It's a gas molecules. They're gas. There has a lot of oxygen, nitrogen, and CO2. I mean, doesn't matter. The air is a molecules of that. There's a lot of molecules in the air. Okay, so they do transfer to the other object. Okay, yeah. So don't forget the air also containing something. Okay, yeah. So this is, they always transfer from higher temperature to the lower temperature. In another word, okay, so let me just see. Once you open the refrigerator and you feel cold, what happens? It's not the cold air coming to you. It's because the cold refrigerator is sucking the heat from your body. So that's why you feel cold, because you're losing energy. You're losing the heat. The heat is coming from you, and you transfer the heat from your body to the refrigerator. So the refrigerator will gain the energy, gain the heat, but your body is losing heat. So you feel cold. Okay, and right now, constantly we're generating heat to the environment because the room temperature is much lower than the temperature in our body. Okay, so we're constantly losing the heat. Okay, so that's why you need to wear clothes. Okay, it's not because something we have to protect, but I mean, we're losing heat all the time. Okay, the animals don't have to because they have fur. They have long enough fur, so they can protect the heat be transferred. But we can't, okay, we can't. So you have to keep the energy, and also you have to keep constantly eating food to gain the energy in your body. Otherwise, how come you can keep your energy sustained every day? Okay, yeah, so again, so this is a heat flow. Remember, have to from high temperature to the low temperature. It really doesn't matter what is the big size of the object or not, but the temperature always from high temperature to the low. Okay, in another word, for example, if you have a bucket over here and you're tossing a very tiny small hot metal over there in the water, in the cold water, then you know what happened. Well, when this hot metal into the cold water, the hot metal will losing the temperature, right? The temperature of the metal will decrease. So that means the heat is being transferred from the small tiny object of this metal to the water, right? It's transferred. The heat is being transferred. That makes sense, right? So in another word, the water should gain the heat and raise the temperature. Does it make sense, right? Right. So the metal will decrease. If we talk about the temperature, the metal will decrease temperature, and this is the temperature of the water, and this is the temperature of the metal. So the temperature of the metal will decrease, and the temperature of the water will increase. And then, just telling you, eventually they are going to equal together because they're going to match the temperature. So the final temperature, the temperature of the metal and temperature of the water will equal. And then when the temperature is equal, there's no more temperature transfer, the heat transfer between the two objects. Does it make sense, right? Because the heat is transfer is making the temperature change. So if there's no temperature change, that means there's going to no heat change. Does it make sense? Okay, so this is a concept. At first, you're gonna understand the concept, and then in the future, we're going to using this concept to doing the calculation. Okay, but first of all, you need to understand the concept. Make sense, right? Heat transfer is because they have a temperature difference. Okay, no temperature difference, then there's no heat transfer. Okay, and the heat transfer should transfer from one to another. The heat, which means the energy will never destroyed. Okay, the energy will never destroyed. They are only just doing the transfer from one object to the other object. Okay, so the metal losing the heat, in another word, the water should gain the heat. That makes sense, right? If this is a closed object, which means there's no heat going to outside, but inside the metal should lose the heat, but the water should gain the heat. That makes sense, right? This is another important concept. Okay, let's take a break. Okay. Okay, so here's my thought. Okay, next week, I'm going to open my office hour. I mean, I will send a form to everyone, or like a Excel spreadsheet, the shared Excel spreadsheet. I'm going to open my hours, office hour, okay, and then we're going to meet. I hope I can individually meet everyone and discuss your progress, your progress in this class. Okay, yeah. So I would like to talk to every single person. Okay, and then go review the things in chemistry. Okay, it won't take too long, probably 5 minutes or 10 minutes. Okay, what do you think? 5 minutes enough or 10 minutes? Yeah, so I'm going to just open the slot for everyone, and then I can send the shared spreadsheet, and then you just sign in, okay, which part you're available, and then we will meet at that time. What do you think? Okay, yeah, okay, so do you think 5 minutes or 10 minutes? Probably 10 minutes?
Probably 10, yeah.
Yeah, okay, yeah, so this is my plan. Okay, I hope I can meet everyone, and then we talk about, we discuss, okay, what's your plan in the future? Okay, yeah, since the class already go to the half, okay, we have another half to go. Okay, so you still have a chance to get a better grade. Okay, yeah. All right, so, or if you have any idea, send me email. Okay, yeah, but this is my plan. Okay, I send you a shared spreadsheet, and then you sign up. What's the time you're available, and then we will meet at that time. Okay, yeah. Okay, so now we talk about the two and the heat transfer. The heat can be transferred, and the heat will changing the temperature. If you gain the heat, you increase the temperature. If you lose the heat, you decrease the temperature. Okay, yeah. So the heat is the amount of the energy that is used to changing the temperature, either is up or down. Go up, you're gaining the heat. If you're go down, which means you're losing the heat. That makes sense? Okay. Yeah, the next part, we're going to talk about two different kind of the chemical reactions or chemical or process. It's called exothermic reaction or process. The other one is endothermic reaction or process. Okay, exothermic reaction or process. The reason we call it process is because some of the physical process can also be endothermic. Okay, yeah, or exothermic. So it could be, this process could be chemical process, could be a physical process, but that's a exothermic or endothermic. Exothermic is talking about this process, they're producing heat. Okay, in this, so the system, okay, so now we talk about the system is releasing heat, is a release heat. Okay, system is release heat. In another word, the surrounding should gain the heat. Okay, and when we talk about system and surrounding, those two is coupled. Okay, if the system releasing the heat, then the surrounding must gain the heat. Okay, those two should coupled. Okay, for example, if we have some object, right, and then if this object is producing heat out, then if we see the object is what we observe, and this guy is a system, and when this guy is releasing heat, and so the surrounding is in the outside, right? Surrounding is in the outside. So you can see now system is producing heat out, they're releasing heat, the surrounding that gain the heat. Then my question is, the system will the system losing or gain the heat? System.
Oh,
System will lose the heat because they produce the heat out, right? This guy losing the heat, so the system will have a lower temperature, right? And the surrounding will gain the heat, so the surrounding will have a higher temperature, right? So then this is called exothermic. Like example is like a burning wood. You have a pile of the wood over here, pile of the wood over here. So this guy, the wood, has a combustion reactions over there, right? So they're going to producing the heat out. So if you look at the system itself for the burning wood as a system, and the surrounding, for example, you, this is you, you're sitting over here. Okay, you're sitting over here. So you feel warm, right? You feel warm. That's because you absorb the heat. You're getting the heat, so you feel warm. But you are the surroundings, right? You're the surroundings. If we look at this, the burning wood is the system, but you're the surrounding. So your surrounding is gaining the heat, but the burning wood as a system is losing the heat. Does it make sense? Right? Okay, so how do we represent that? We're going to just write the heat of the system will getting loose. We're losing the system. So that's going down. Okay, the heat of the system is getting down, but the heat of the surrounding will going up. Okay, again, the heat is not being destroyed. One is losing the heat, the other one must gain. Okay, yeah, one is losing the heat, the other one must gain. Does it make sense, right? Okay, yeah. So this is called the exothermic, which means the system is releasing heat and the system will losing the heat, or system release or lose. Generally, is talking about the same thing, okay? Release the heat or lose the heat is the same thing. This is called the exothermic reaction. So all the combustion reaction can be seen as the exothermic reactions, okay? All the combustion reaction. Let me just write on the other side. Exothermic reaction, which means they are going to absorb, they are going to produce the heat out, right? Like a firework. If you see the firework, that's also a combustion reaction. I mean, when the things explode, they actually generate quite a lot of heat to the surroundings, right? Yeah, so if you see everything, as long as it can be explosion, then the definitely is the exothermic reaction. They're producing the heat out. Okay, they're producing the heat out. So this is the exothermic. So let's move this part down. Yeah. So the reason we're talking about the process is some of the physical process can also be exothermic, okay? Can also be exothermic. For example, okay, so if you have from water to ice. This process from water to ice. Okay, yeah, from water to ice, you can see this guy. This is also a exothermic process. Okay, water to ice. This process we call this is called freezing. Freezing process. The freezing is also exothermic. Why? You can think about what is the temperature for water? It's above 0 Celsius. And what is the temperature for ice? It's below, right? Yeah. So after the process, they have from high temperature to the low temperature. That means the system is losing the energy. That makes sense, right? So this process is an exothermic process. Okay, the system is losing the heat. So that is why this guy is called the exothermic process. Okay, yeah. But in general, we have 3 different the state, right? Gas, liquid, and the solid. And usually gas always has a higher temperature. I'm talking about the same object. The gas always has a higher temperature than liquid, and liquid always has a higher temperature like gas, like solid, than solid. Just like water vapor, water, and ice. Okay, so the gas molecule always has a higher energy than the liquid state. The liquid always has a higher energy than the solid. So from the top state to the bottom state, they always is an exothermic process. Okay, although this is a physical process, but they can also be exothermic. So the definition of the exothermic is the system is releasing the heat, or the temperature of the system will decrease. Okay, yeah. So from gas to the liquid, they're having exothermic. From liquid to the solid, also exothermic. So this is what we talk about exothermic. Okay, very important because we're going to use this a lot. The system losing the heat. Okay, the system losing the heat, or surrounding gain the heat. Those two are coupled. Okay, yeah. There's a different way the system can losing the heat, but as long as the system losing the heat, then that's called the exothermic. Okay, yeah. The next one is called endothermic. Well, exothermic, endothermic, those two are coupled. So endothermic, that means the system is not losing, the system gain the heat. System gain the heat, but the surrounding lose heat. Okay, system gain the heat, but surrounding losing heat. That is called the exothermic process. Okay, so this is called the exothermic process. Yeah, this is called the exothermic. This is called the endothermic process. System gain, surrounding lose heat. Or you can say since system increase the temperature, but the surrounding decrease the temperature. This is also exothermic. Okay, can you imagine what is the situation is endothermic? Sorry, what is the situation for endothermic?
Yeah.
Ice melting, yes, yeah, ice melting. ice melting, okay, the ice has a lower temperature, but when they absorb the energy from the surroundings, they're going to melt, okay? The temperature of the ice is increased. So this is endothermic, of course. This is endothermic process. Okay, endothermic process. So in another word, if you look at, see, from higher energy state to the lower energy state, that's exothermic. But if you go upwards, which means if you go from lower state to the higher energy state, then this process are all endothermic. Those are all endothermic process. Okay, yeah, because they need energy. Okay, they gain the energy and then the process. Okay, so ice melting is from solid to the liquid, or you can from liquid to the gas, boiling. Okay, or we call the vaporization, right? You cannot have the water. I mean, you cannot put the water boiled. I mean, we cannot have automatically boiled water, right? You have to heat the water, and the water absorbs the heat from the stove, and then the water will start to boil. That makes sense, right? So you have, this is endothermic because they need energy, okay? Or just like if you open the refrigerator, if you look at the refrigerator is gaining the energy from you, right? So the refrigerator actually is also the endothermic process because they are absorbing the energy, okay, from you. But if you look at yourself as the system, then yourself will be the exothermic because you're producing the heat out. I know here, this is a concept. So endothermic and exothermic is really depends on what kind of system you're looking at. What kind of system you're looking at. Hopefully I did not confuse you. Did I? No? Okay. Yeah. For the thermal chemistry, when we talk about endothermic process, it's easy to understand. So what a chemothermic reaction is the same thing. When you do the reactions, the reaction is absorbing the heat. Okay, so the surrounding will getting cold. But this reaction, it won't. I mean, it's not very obvious. It's not like explosion or something. Okay, yeah, they're very, very minor. So now I'm going to show one of the video and give you the sense what is the endothermic chemical reactions. Okay.
What I have is some barium hydroxide. Okay, I'm going to put this into barium hydroxide, and I've got some ammonium chloride. Now what I'm going to do is mix this together, and hopefully we should see an endothermic reaction. Yes. What hand side? The hand. Oh, it's just this one, I guess. I was chopping on hearts earlier. Yeah, I need to be not covered in blood. So what I'm going to do to show how exothermic is, how much heat is taken in, I'm going to make this wooden block wet. Okay. Now, you will see why I've done that in a second. So I'm going to mix these two things together and carefully mix these two things together. Well, hopefully not, because if it's blowing up and giving out fumes or anything like that, that would be what type of reaction? Exothermic. Now we want endothermic, so it's going to be a little more subtle. So I mix the barium hydroxide and the ammonium chloride together, and they should start to react. Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you see actually that's all liquid, and it was all just solid powders. It's not milk. You wouldn't want to make it. Okay, you put that in coffee. Oh, from these problems. Now, one of the products of this, because it's ammonium chloride, is it's spinning off ammonia, which smells rather horrible. And I forgot about that, which is why I just breathed these ideas. that whole sort of horrible, slightly tangy smell from wheat is sort of ammonia like.
Oh, is that what?
Yeah, that's what you can smell. Unless you wet yourself, that is smell. Okay. But also, actually, this is getting actually very cold. It's going along. Okay. Now, hopefully, this has worked. It's getting cold enough. Well, if you now put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well. So much energy has been taken out of the environment. So that water is so cold, it's dropped below freezing, it's frozen onto the bottom. That's pretty cool. Well, I haven't. In fact, I haven't looked at one actually. Right. So I put that there. That is dropping down to. Well, we know it's below what? 0. So this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going. If you had it on there, yeah, it would start to. But in fact, there's actually ice crystals forming inside.
Okay, so that is called endothermic. Okay, yeah. So you can think about why they're going to those two are glued together. They're having a block over here, and they put the liquid water over there, right? So if we talk about chemical reaction, and the reaction is as a system, which means the reaction is inside of the bottle and the beaker, right? So the reaction is a system. So the rest of the others is all surrounding. And this is an endothermic reaction, which means this reaction is absorbing the heat. So making the surrounding has a lower temperature, including the water parts. The water is also surrounding, right? So the water have a lower temperature and below the freezing point. So the water start to freeze, start to freeze, right? It's called a freeze, not frozen, right? It start to freeze. So then they're going to just like a glue together between the beaker and the block. So that is why you can see those two all together. Okay, yeah. So this is one of the very typical endothermic reactions. A lot of the lab or in the university, the professor usually will do this kind of demonstration. This room is so tiny. If we do making the ammonia out, then everyone will be. Okay. All right, so this is endothermic. Okay, are you clear? Endothermic, the system gain the energy and the surrounding losing the energy. So that is the endothermic. All right. So if we write this endothermic, you can see, okay, Q is the heat. So the system of the heat is a gain, but the heat of the surrounding will lose. Okay, again, heat will not be destroyed. Something gain the heat, must something gonna lose the heat. Okay. Okay, so the next part, we're going to talk about the sign of the heat. Sign of the heat. The heat could have a sign, okay? So when we talk about if the heat is a positive, which means if the heat is a positive, okay? And so this generally is talked about is endothermic. If it's a heat is smaller than 0, which is negative, and this is exothermic. This is exothermic. So what does that mean? The heat is transferred, is being transferred. Why the heat is a positive is endothermic. Is the heat positive? That means the system is gaining. System gain the heat. System gain the heat. So that is why one with the positive number is a gain. Okay, if the heat is a positive, that means the system gain. This everything is talking about system. If it's a negative, that means the system lose. Okay, so system lose the heat. Okay, so that is why if the Q is larger than 0, that means the system gain, because the heat of the system getting more. So this guy is a positive. If it's negative, that means we need to subtract the heat. So the system is lose heat. That means make sense, right? Okay, very important, because we do test. Okay, what is the positive mean? What is the negative mean? Okay, positive, that means this is a endothermic. Negative, that means it's an ectothermic. Okay, yeah. Okay, we will talk about this later. Okay, yeah. So positive is endo, negative is exo. Okay, negative, that means this guy is losing the heat. Positive, that means they gain the heat. Okay, yeah. Okay, so the next one is talk about the unit of the heat. The unit of the heat. Okay, so in general, when we talk about, okay, what's the unit that represent heat? Generally, in chemistry, we're using joule, this unit. Okay, this is a SI, international system. Okay, international system. We're using joule as the energy. So this is the unit for energy. But the point is, joule, this unit is too small. In chemistry, we usually using kilo. So the unit is J. We're using kilojoule to represent. In a lot of chemical reaction, we're just using kilojoule instead of joule. Okay, yeah, because the joule unit is too small. So 1 kilojoule is equal to 1,000 joule. Okay, so hopefully you can convert. The kilo is the same thing, right? Kilogram, that means 1,000 grams. 1 kilojoule, that's 1,000 joule. Okay, so this is the unit for the joule. Okay, and we also has another unit, but we rarely talk about. One is called a calorie. You probably say, "Oh, I hear that. I heard that before." Okay, calorie, but this calorie probably is not a calorie you're talking about. Okay, this calorie is not equal to food calorie. Okay, so this calorie is also a small unit. The definition of this calorie is the energy that's needed to raise 1 gram of water by 1 Celsius. Okay, so this is the calorie meaning. The calorie is also a small unit. Usually 1 calorie equal to 4.184 joule. Okay, 1 calorie equal to 4.184. But here I need to mention here this calorie, that should be a small case, small c instead of, okay, small c. Okay, so 1 calorie equal to 4.184 joule. Okay, the next one is the unit that we commonly know. It's called the food calorie. And this K calorie is using capital C. Okay, so we also call this as a kcal. We also call this kcal. So food calorie and this calorie is different. Food calorie, 1 food calorie or 1 kcal is equal to small 1,000 small cal. Okay, So there, this is 1,000 times difference. Okay, 1,000 times difference. Okay, so if you see 1 food calorie or 1 kcal, that's equal to 184 joule. Okay, so that is the 1,000 times difference. Okay, so this is a kcal. And so when we talk about the food calorie, and when you have the doesn't matter what kind of food, in the back of food it shows what is the energy that you talk about, and that energy, that is the energy we talk about here, food calorie. Okay, so 200 something cal, and that is the food calorie. It's not the small unit calorie. Okay, it's not this calorie, it's the food calorie. Okay, yeah, and our body normally we need at least 2,000 cal, right? 2,000 kcal to sustain. Okay, well, you don't have to be talk about sustain. So that means if you eat less every day, your size will shrink, right? Yeah, because your body will build, your body need energy, but the body will produce more energy than you're taking. So the body will consume some leftover in your body, and then you will be healthy. Have you ever seen? Okay, sometimes if you're be hunger, it will make you have a longer life. You will be healthy. Yeah, this is recently the people studied. Okay, yeah, if you eat less or you keep hunger, and you will be healthy. Okay, and you live your life longer. Okay. Okay, so let's take a break, and then we will talk about the last concept, and then we're done for today. There's a good football game on for college. Baylor versus West Virginia. There's some really good college games. You watching college? They seem to play a lot harder, more aggressive. I think it's funny to see freshmen get smashed by 7-year seniors. You're either in sports if you want to sports, or you're not. You go to I like diving. So like the ultra diving. Yeah, yeah. I think so. Or maybe not. It had, but it had like, yeah, it was like bird's eye view. Okay, so the last concept we're going to talk about is specific heat capacity. And this probably you heard that before, but most of you probably not, okay? Today we're just to talk about a concept, and then next time we're going to use the concept and doing the calculation, okay? So it's called specific heat capacity. A lot of people call the specific heat, or people call it SP heat. Okay, so a lot of different concepts. If you want to search online, those three things, I mean, search on YouTube, those three are all talk about same thing. Okay, specific heat capacity, specific heat, and SP heat. They're talking about same thing. And when we talk about this concept, we're using capital C to represent capital C. This is a capital C to represent the specific heat. Okay, so this is the specific heat. So what does that mean of this specific heat? If you're just looking at the capacity, what does the capacity mean? The limits, how much they can occupy, right? Okay, so heat capacity generally talk about how much this guy can occupy the heat, right? So how much they can occupy the heat, okay? So generally this, but what is the definition? The definition here is a specific heat is the amount of heat required to raise 1 gram of an object by 1 Celsius. Okay, yeah, I know sometimes it's hard to understand what does that mean. Okay, yeah. So first, go ahead, write this definition down. Then let's just explain that one by one, okay? Amount of the heat. Okay, so generally, specific heat is the amount of the heat, but they have a requirement, okay? So we need this heat. This heat is used for what? It's used to raise the temperature of this object by 1 Celsius. And 1 gram of this object by 1 Celsius. Okay, well, different object may have a different specific heat. Okay, yeah, so that is why if you're giving the heat to different object, they're going to increase the temperature in the different speed. Some of the raise the temperature very quick. Some of the raise the temperature very slow. Okay, that's because they're having the different specific heat. Okay, they're having the different specific heat. And for the specific heat, they are having the unit. Let's see the unit. Unit, this one is the combined unit. Is talk about this is a joule divided by gram and divided by Celsius. Okay, divided by gram divided by Celsius. Or you can talk about joule divided by gram divided by Kelvin, okay? So the Kelvin is the unit for the temperature, okay? And just so you know, those two units are exactly the same, okay? Those units is exactly the same. Joule per gram per Celsius is equal to joule per gram per Kelvin. Those units are the same thing, okay? You can interchangeable for these cases, okay? So now, let's just talk about some of the common, let's just do one of the search. Okay, you see here, let's look at this table. Okay, so this is the sum of the numbers for the specific heat. Okay, for the specific heat. Now let's just talk about, okay, doesn't matter what is the number mean. Let's talk about what is the big number mean and what is the small number mean. Okay, yeah, you see this guy is silver. Which one is the smallest number? Silver, right? Silver 0.235 joule per gram per Celsius. The biggest number is water, 4.184 joule per gram per Celsius. So what does that mean for the smaller number? That means, okay, I just need to 0.235 joules of the energy, and then we can increase 1 gram of the silver by 1 Celsius. Okay, so I just need a little bit amount of the energy, so I can raise 1 Celsius of the 1 gram of this silver. Okay, but what is the meaning of this the big number 4.184? That means I need to using 4.184 joule of the energy to raise 1 gram of the water. So we compare to silver and water. I mean, water need more energy to increase 1 Celsius, right? So if you look at the difference, it's almost like 20 times difference. Okay, almost 20 times difference. In another word, if I want to increase the water by 1 Celsius, I generally can increase 20 Celsius of the water silver if we're adding the same amount of the energy. Okay, so that means if we heat up the silver and the water, definitely silver gonna raise up much faster than the water. Does it make sense, right? Okay, so now here we have the look at just based on those numbers. My question is, okay, which materials is the best for cook well? And what is the meaning for the cook well? Okay, you know what is a cook well, but what is the specific function for the cook well? The cook well, you're using the cook well to heat the material, heat the food, right? So if the temperature of the cook well did not increase very fast, then or this is not good for you, right? You're gonna wait quite a long time to do so, right? Yeah. So generally, the good cook well should have a very low specific heat. Okay, they're going to transfer the heat very fast. Okay, so based on here, you can see silver gonna be the best option for the cook well. But did you see the silver pan? Probably not, right? I know King maybe have a gold one. Okay, yeah. So well, this is pretty expensive, so nobody use it. So the next option is going to be copper. Okay, yeah. So a lot of materials, the very good cook well containing quite an amount of the copper in there. Okay, yeah. So usually the copper cook well is much better than the iron cook well. Okay, yeah, and also more expensive. But if you don't have the money to afford for the copper, then you can choose iron or steel. Okay, iron and steel are similar. Okay, so and also iron has very common in the world, in the earth. So that's why you can find a very cheap the cook well made from iron. Okay, made from iron. Okay, so that is the meaning for the specific heat over here. How much heat you need to increase the temperature. Lower number, that means you just need a little bit of heat to raise up those materials by 1 gram. The higher number, that means you need a lot of energy to raise up those materials by 1 gram, by 1 Celsius. Okay, so now let's talk about the water. Okay, what is the application that we can use for water? Water has a very high specific heat. That means we need quite a lot of energy to let the water raise from 10 Celsius to 11 Celsius, right? They need from 10 Celsius to 30 Celsius. They need quite a lot of energy, right? So the beauty of this high specific heat object is they can absorb quite a lot of energy and still keeping cool. Did you see in the hot, I'm not sure, did you see on the Amazon, you can buy some of the materials. Is cooling even in the very hot temperature. Okay, it still feel you can still feel cool. Okay, those materials has a very high specific heat, just like water. That is why you go to in the summer, you like go to the swimming pool, right? You like to go to the ocean, go to the lake, or you go to the river because the water is cool. Well, the thing is, water will receive the same heat just like the other dirt or something, but the dirt usually has a much higher temperature than the water. It's because the water needs quite more energy to increase the temperature. So although you're receiving same temperature, same heat, but the point is the water will increase the temperature slower than the other stuff. So when you go to the swimming pool, you still feel very cool because the water still have a lower temperature than other object. That makes sense, right? Yeah. So that is why on the two coast, west side, east side, their temperature usually is cooler than the middle, the heart of the land. Okay, the heartland. So we're so miserable in the summer. Okay, yeah. Anyway, so this is the function for the water. Okay, and also just let you know, a lot of the very big air conditioner, they're using water as the cooling system, as the cooling system. Okay, yeah, they're using water, a lot of water as a cooling system. Okay, yeah. So this is a function for specific heat. Okay, lower number of the specific heat, that means we're gonna raise the temperature very fast. Okay, large number of the specific heat, that means we're gonna need quite a lot of energy to raise the temperature by 1 Celsius. Are you clear? Okay, so this is the definition for the specific heat, and we are done for today. Okay, I already sent an email for today's lab. We're going to do lab 30. Okay, we're going to lab 30.